In the late 19th century, as cities around the world flickered to life with their very first electric lamps, a new idea began to sweep across the landscape. An idea that would redefine how humanity distributes the energy that powers its civilization. Alternating current, AC. It arrived not as an incremental improvement, but as a radically different approach. A pulse of energy that reverses direction, rhythmically, 50 or 60 times each second. A current that seemed almost alive in the wires, oscillating, dancing, reacting. To many engineers of the era, AC was not merely a technology. It was a promise that electricity could travel farther, reach more people, and illuminate entire nations. But like every breakthrough in history, the truth is more complex. AC became the dominant standard for over a century, not because it was perfect, but because it solved one very specific problem spectacularly well: moving electricity across long distances. And yet, beneath the surface, inside our homes, inside our devices, and inside the modern renewable grid, the limitations of AC have never fully disappeared. Today, we explore the strengths and the weaknesses of alternating current. Part 1. Why AC won the first war. When electrical engineers speak about AC, they often begin with a single, simple concept: the transformer. A silent, elegant device that can raise voltage to enormous levels and lower it back down safely on the other side. High voltage means less current. Less current means dramatically fewer losses over long transmission lines. In the era before modern power electronics, this was a revelation. Where Edison's DC could barely reach a neighborhood, AC could cross mountains. It could power a city from a river hundreds of kilometers away. It could link entire regions into a unified electrical network. This was the triumph that changed everything. And so, in the great power stations of the early 20th century, from Niagara Falls to the industrial heartlands of Europe, turbines spun massive AC generators that fed grids stretching farther than anyone had ever imagined possible. For its time, AC was a masterpiece of practicality. But technology moves forward, and the world today is not the world Edison, Tesla, or Westinghouse lived in. Part 2. The hidden costs of alternating current. The same characteristics that made AC so powerful in the past have become challenges in the digital age. Because AC isn't smooth, it isn't constant. It is a repeating wave, rising, falling, reversing, dozens of times a second. That rhythm creates a series of physical consequences. 1. Reactive power. AC systems don't only carry real, usable energy, they also carry reactive power, energy that oscillates but doesn't do work. Reactors, capacitors, inductors, motors, fluorescent lights all distort the wave. Engineers must constantly balance these disturbances to keep the grid stable. 2. Harmonics. Modern electronics, computers, LED lights, chargers, consume power in pulses. These pulses create harmonics, distortions of the AC waveform that heat transformers, overload lines, and waste energy. 3. Frequency sensitivity. An AC grid depends on maintaining a precise frequency. In a 50 Hz system, every generator and load must match that rhythm. If the frequency drops too low, grids collapse. If it rises too high, equipment fails. As renewable energy expands, this challenge becomes harder, because wind turbines and solar inverters don't naturally oscillate at grid frequency. They must be forced to imitate it. 4. Difficult storage. Perhaps the most overlooked weakness: you cannot store AC. Only DC can be stored. Every battery, every solar panel, every electric vehicle, every modern data center works internally on DC. This means AC requires continuous conversion, and every conversion wastes energy. Part 3. AC in the age of renewables. When AC was invented, energy was produced by giant spinning machines. steam turbines, hydroelectric wheels, gas generators. These machines created AC naturally as a consequence of their rotation. But today, the world is changing. Solar panels generate DC, batteries output DC, electric vehicles charge and discharge DC. LED lighting, computers, home appliances, even refrigerators all convert AC to DC the moment it enters the device. A century after the triumph of AC, our homes have quietly become DC environments, pretending to run on AC. And this mismatch creates enormous inefficiency. Every inverter, every rectifier, every converter, from rooftop solar systems to laptop chargers, turns precious energy into heat, and sometimes noise, distortion, or electromagnetic interference. On a global scale, these conversion losses add up to staggering amounts of wasted power. In a fully renewable future, AC becomes even more complicated. Wind farms often generate wild AC at variable frequency. Solar farms produce DC that must be inverted. Grid operators must work harder to stabilize frequency with synthetic inertia, something AC never originally required. In a world of distributed, renewable, flexible energy, AC is no longer the obvious champion. It is the legacy standard. The question now is not whether AC was important. It clearly was. The question is whether AC still makes sense in a world that thinks, stores, and lives in DC. Part 4. AC's remaining strengths. To be fair, AC still possesses formidable advantages. 1. Transmission efficiency at very high voltage. High voltage AC transmission, HVAC, is still widely used worldwide. 2. Grid familiarity and infrastructure. Replacing global AC grids overnight is impossible. 3. Rotating machinery compatibility. Heavy industry still depends on large induction motors built for AC. These strengths are real. They are why AC still surrounds us today. But the modern question is, for how long? Part 5. The emerging shift. Around the world, a quiet transformation is beginning. HVDC transmission lines, once rare, are now the backbone of long-distance renewable networks. DC microgrids are emerging in data centers, airports, and industrial campuses. Electric vehicles, storage farms, and solar arrays form vast DC ecosystems, connected by AC only because history demands it, not because physics requires it. The irony is striking. AC won the 19th century, but DC may win the 21st. Alternating current is one of the great inventions of modern civilization. It empowered nations, connected continents, and illuminated entire cities. Its simplicity, elegance, and practicality made it the perfect solution for an age of centralized power stations. But technology evolves, and as we stand at the threshold of a renewable world, one built on storage, solar, computing, and electric mobility, the limitations of AC are becoming clearer. This is not the end of AC, but it is the beginning of a new debate. A debate that asks a simple question: is the system we inherited the system we need? Or is it time to reconsider the current that flows beneath our cities?